Hi, and welcome to the Space Industry Podcast by SatSearch. My name is Narayan, COO at SatSearch, and I'll be your host as we journey through the space industry. The space sector is going through some seismic changes, promising to generate significant impact for life on Earth and enable humans to sustain life elsewhere in the cosmos. At SatSearch, we work with buyers and suppliers across the global marketplace, helping to accelerate missions through our online platform. Based on our day-to-day work supporting commercial activity, my aim here during this podcast is to shed light on the boots on the ground developments across the globe that are helping foster and drive technical and commercial innovation. So come join me as we delve into a fascinating, challenging, and ultimately inspiring sector. Hi, and welcome back to the Space Industry Podcast. Today we're going to be speaking with Michael Seidel and Adrian Helwig from Texas Instruments. Texas Instruments, in short TI, is a global semiconductor manufacturing company with expertise in analog and embedded processing chips. TI's space portfolio includes over 270 active components. Michael and Adrian will be speaking specifically about the benefits of standard architectures for space missions in this particular podcast episode. Michael and Adrian, welcome back to the Space Industry Podcast. It's great to have you guys back here.
Yeah, good to be here again.
Thanks for having us.
Great. Today, we're going to be talking about the benefits of standardized architectures for space missions. And when we're talking about standardized architectures, it obviously makes sense to talk about what are standardized architectures in the context of space missions. And beyond that, what are the specific advantages that they actually bring in? So if you can kick off from there, it would be great.
Sure, I can take that one, no problem. So really, in space missions, if we talk about standardized architecture, it means using common modular system designs with standardized interfaces and form factors. And this really ensures that different components from different manufacturers can work together reliably. And as an example, I can give you two different standards. For example, the SOSA Space VPX standard, which means Sensor Open System Architecture, is one example. If you want to go to the European Space Agency standard, there is also one called Advanced Data Handling Architecture standard. So those are two space standard examples. But as well, maybe to give you an example from commercial world, if you think about a USB port, right, in consumer electronics, it's really, regardless of the manufacturer, if it follows the standards, you can be sure that it will plug and function as expected. So that's really the beauty of standardization. And why is this all important? Well, there are different advantages. First of all, shared research and development cost. Because if your development costs are getting spread across different mission and programs using the same architecture, you are definitely sharing your cost and bringing the cost down. Another point, which is economies of scale, it's also very important because now if you are producing your standard components with higher volumes, this means naturally that your per unit cost is going down, right? And this is especially important in space where your hardware tends to be expensive anyway. To give you an example for this kind of mission, a good example would be this low Earth orbit constellation where you have hundreds of satellites that you need to manufacture. And another point which I wanted to mention here is ecosystem of suppliers. Because if you think about this now, if everybody works to the same set of standards, different companies and manufacturers can develop compatible components, right? So that's really economies of scale. And this allows you mix and match environment where really the designer can decide for the best available option on the market and not being locked maybe to one manufacturer which was approved. And finally, let me also mention the technology reused, because if we think about this now, when you have your established and flight proven system, that can be quickly integrated into a new design, maybe with small modification, but you still reusing your existing system. This saves your time and at the same time is reducing your technical risk. So to summarize, in short, really the standard architectures makes the space mission more cost-effective, flexible, and scalable. And this is especially important because the space industry continues to grow.
That's great. Actually, the points that you made of shared R&D costs, economies of scale, having a diverse set of supply chain partners and the technology we use are obviously very impactful in the context of also many new players entering the market. So we are seeing today a diverse set of applications and them turning into constellations that are entering the market. So obviously, this is now creating a leverage and also a competition within the supply chain in itself. So do you agree with that assessment, firstly, from a TI's perspective? And if so, then what this competition means for space engineers and mission designers?
Yeah, I would say absolutely. It's getting more competitive. It's getting harsher there. So there's definitely a growing number of new entrants and players in the market. And that means people need to get faster. Time to market matters a lot. And that causes then typically the need for specialization, right? You need to know your playing field to enable really the best possible progress and innovation and be really significant here. And along those lines, as Adrian mentioned, reusing your R&D efforts. And one thing, bring the cost down, but also it makes you much, much faster on it. And therefore, at TI, we really want to make sure we are enabling these hardware platforms that really scale across multiple projects and multiple missions and multiple use cases. So like, for example, our TI design proposals or hand design proposals typically target, on the one side, multiple mission profiles, but also maybe when it comes to power supplies or motor control, a wide range of voltages and power levels for different types of motors and actuators. Or when you talk about RF, then we want to make sure we support different frequency bands from a single platform. And all that, of course, as said before, increases also your purchasing volumes, bringing the cost down and makes you overall more competitive.
And one of the analogies that I have seen often recently repeated is this analogy to the automotive industry, where basically the automotive industry, starting from the 1900s, going towards standardization and volume production, and space may be taking that particular journey, where basically because now there is volume in production, there's a lot of comparison that people are trying to do, saying that the standardization and the production approaches that the automotive industry has taken to meet those kinds of volume demands and lowering cost and increasing reliability is actually something that people want to see happen also in the space industry. What do you actually think about this comparison? Obviously, TI has a deep knowledge of both of these industries, having worked there, and there's probably you are in the best position probably to answer this. So, what are the similarities and the differences that you will see between the two?
Yes, it's a really good comparison in some ways because both industries face similar challenges when it comes to system complexity, reliability demands, and also the need for efficient production and supply chain. But there are also some significant differences. But let me start with the similarities. Both industries have the need for standardized architectures. And let me add one comment here. Space may not be as standardized as automotive at the moment, but the need is still there. So both need to build ecosystem of suppliers, which I already mentioned, to enable this mix and match approach for their subsystem and components. And that will allow flexibility in both automotive and space industry. There is also a similar cost and time pressure in both industries. So as already mentioned, they both need to spread their R&D spendings across multiple programs. And because the quantities in space are even much lower than in automotive, you need to even put more focus on reducing this R&D costs. in space. There is another point which I wanted to mention is a need for integrated diagnostics and self-test capabilities. If we talk about automotive, that's really about safety and maintenance. In space, it's about more ensuring reliability in environment, because you cannot send a technician, right, to the space to fix things. That's simply not possible in space. You relied on this integrated diagnostic and self-test capabilities. Very important point, which I wanted to mention here as well, is that both industries have a constant pressure to access really the greatest and latest semiconductor technologies, simply to drive the innovation. And what is interesting, companies like Texas Instrument play in both spaces. So we can bring so-called cross-industry expertise, and we can transfer technologies from one industry to another one. And every year, we are bringing really a high number of new qualified parts. For automotive, it would be Q100 parts. And for space, we have special space qualified components. Now, on the differences side, one very important difference is the environment. It's far harsher in space compared to automotive, because the components, they need to withstand extreme temperature cycles. And not to forget, there is also radiation, which is not present at automotive. And because of that, for space, we need a dedicated product and components. As an example, a car platform, if we think about this, a car platform life cycle is maybe 7 to 10 years. But space platforms can stay in demand for decades. It's very common for us that we are receiving orders for components that have been in space for more than 20 years, on the market for more than 20 years. That's very common practice. So this means that we need a long-term component supply and consistency. That's very important. And even to add on that, the space missions have often to support a different profiles. You have a low Earth orbit mission, you have geostationary orbit, and each mission comes with their own duration requirements. For that, we also offering specialized products like QML Class V components, QML Class P, as well as the space enhanced products for LEO missions. And those products really help balance those needs. And another big difference, which I wanted to mention at the end, is the range of application in space. Because automotive is a really consumer market with pretty predictable use cases. But in space, you are serving everything from telecom, navigation, defense system, deep space science, a radar application, and each with its own demands. That's the reason why TI is bringing a very wide range of products for space to the market. So in summary, while those industries are sharing some fundamental principles around standardization, reliability, and production efficiency, space adds really unique challenge in terms of environment, longevity, volume, and application diversity. And that's really the addition, even if those markets are sharing general rules.
Great. That's actually a very nicely put summary of the two comparisons of the two industries. As you mentioned, there are some specific challenges that come up in the space industry, especially given the diverse set of missions, starting from just flying satellites to actually flying humans that then come up, or flying satellites within the Earth orbit versus flying satellites back very far out into the solar system. So because of this diversity in applications and the kind of platforms as well, there's obviously going to be a diversity in advanced standardized architectures and the requirements for it as well. So now, how is a semiconductor company like TI adjusting to the requirements in the market for such advanced standardized architectures?
So as said, there's definitely a need for dedicated products for space. It is a very harsh environment, much harsher than what we know on Earth and what the automotive market would require. So if you look maybe for an example like LEO satellites, they take only some 90 minutes to go around the world once. And then when exposed to the sun on the satellite surface, you have probably some plus 150 degrees Celsius. On the other side, in the shade of the Earth, you're down to the minus 150 degrees Celsius. And you do this every 90 minutes up and down. So there's an enormous mechanical and temporal stress on the components. And during launch, there's enormous vibrations that our parts have to resist. So all that mechanical stress right there needs really dedicated materials. And the most prominent example is probably in automotive, people start or try to use copper bond wires. Ideally, this is much cheaper than gold, but in space, that's really no option for us here. And on top of the environmental stress just described, and there's also the radiation hardness assurance, of course. And that is, of course, something that really has to be characterized and identified and verified. And TI has here a very wide product portfolio. We really offer all kind of power management devices, converters, LDOs, load switches, P-driven controllers, gate drivers, voltage supervisors, you name it. Also in the signal chain, right? We have a full portfolio for precision signal chain, either for high-end scientific purposes or for monitoring purposes in the telemetry, telecommand portion of the systems, but also the high-speed signal chain, high-speed data converters up for the X-band support in the 10 gigahertz area, clocking capabilities for these RF things and more. And there's also sensing, monitoring, temperature, current, voltage, interfacing and logic is an important topic in the satellites. MCUs. So overall, more than 270 active products are available. And by the way, they're available in the web store. That's also a pretty unique thing GI can offer there, that you can buy high reliability products directly on the web. And so that's the overall product portfolio. So overall, when we look then for the standardized architectures, or we take the support somewhat deeper, there's, let's say, two important reasons for standardized architectures. The one thing is really spreading your engineering cost across multiple projects and enable the fast time to market, and also benefit from the higher procurement volumes, economies of scale. So that's a cost down and cost optimization effort. But the second one is ability to gain the flight heritage over time. But let me first go a little bit deeper again on the spreading the engineering cost across the multiple platforms and projects, because this is exactly where TI's product portfolio comes in, and the two qualification levels we offer here. So the one is we call it SEP, the space enhanced products, and the other one is called SP, space products or full space grade products. The SEP one is targeting the LEO constellations. This is where we balance the cost versus the screening efforts. Typically cuts here at the 43 MeV, 30K rad, and we save the burn-in on these components, keeping the cost at level. And the full space grade components, the -SP products, they're really targeting the missions with highest reliability requirements, like for geo missions, deep space missions, or even human space flights. And there's where we really comply with all the screening required by the QML standards, and typically offer here 100K rad and 75 MeV or even more. And the nice thing now with the latest and greatest QML standard, the QMLP, is that allows the use of plastic products, plastic packaging. That is where we can then even in many cases offer a pin compatible option between -SEP and -SP in the QMLP grade. Let me give you an example. Our latest red hard and red tolerant 14 volt switching regulator family, the PPS7H4011 or 4012, 4013. There we have pin compatible options between SEP and SP, but also pin compatible scalability from the power levels from 3 amps up to 12 amps, and all with a single hardware design, really just mounting options. And or another example is when we look at our reference design, there's the TIDA 010274. That is a RF design with the DAX 39 RF10 and the ADC 12 VJ 5200. And here again, pin compatible options between SEP and -SP. Also, the clocking tree is scalable based on the LMPA 04832 SEP and SP, and also the power tree around it is being scalable between SEP and SP. So that's one way of looking at this. Like, you need to have a platform that really enables your scalability. But the second one I mentioned before is the ability to gain flight heritage over time. And that is where what's coming here into the game is that when we qualify the product, in the end of the day, we all need to accept that the actual environment in space cannot be easily replicated on Earth. We're getting maybe somewhere close to it, but the ultimate test will really happen in the orbit. And really only after several years, you can really claim victory and know that you have really built something that can spin up there. And so once that hardware is proven with space flights, then people really want to lean against it again, want to buy it again. And that is where new orders for the very same hardware can be very lucrative for the manufacturers. But in order to make that happen for several years down the road, from the semiconductor vendor point of view, we need to freeze the recipe. We need to make sure we have with our space grade product a very long-term supply commitment and hold the recipe and don't change anything there. And we have examples like where we brought the UC1823A, a very popular PWM controller. We brought it in 1995, already 30 years on the market and still shipping and procurable. Or the T1708, a dual non-inverter power driver, released to market in 1997. Or UC1611, a quartz Schottky diode array, released in 1993. So that is what space grade products are. They're there for you for a long time, unchanged. Upscreening is very different. In upscreening, you have a one shot, and especially when you use something that is in high demand. And that is where automotive is probably sometimes underestimated what that really means. If an automotive product is successful, meaning it runs in high volumes, as a semiconductor supplier, there's a high motivation that you need to improve the yield and get the cost down. So there is a permanent move on those things. Of course, we will meet always the data sheet. Behind the scenes, many things are going on. And whether several years down the road, the radiation requirement or radiation performance is still the same or not, is then to be seen. And in automotive, many times you have multiple fabs qualified. So you're really, all bets are off. So that's on availability and flight heritage and all that fed and all the long-term supply. And we're keeping it for 30 years, but people developing something now, they have to be super competitive and future-proof, of course, at the same time. And that is where, from a semiconductor point of view, we need to make sure we give access to the latest and greatest technology capabilities. And when you look at our latest products we've released, AFE7950, that's our RF analog front-end device with an integration level of 6 receive channels and 4 transmit channels to the X-band. So a very innovative product here. Or you have the active balance, the TRF0208, the SEP and SP grade. That spans across the profiles, but also it's scanning across the full frequency range up to the X-band. And with a single hardware design, again, here you can really support all the needs. Another device we just released is the TPS7H6101 SP. That is a radiation tolerant 200 volt, 10 amps GaN power stage. So power stage, power FETs and drivers integrated here. So that is a very beneficial device for all kind of power supply topologies, but also for motor control. So here, again, with a single platform, we can enable motor control for all kind of motors like stepper, BLDC, PMSM. That can be really used here. And finally, let me also mention something where TI is opening a new door for leveraging what we call in other industries functional safety, particularly in automotive. Functional safety, a big topic, and functional safety and self-test capabilities are developed for many of the automotive parts. And now we can bring this even to space with the TMS 570 LC4357 SEP. We have a 300 megahertz dual core lockstep MCU, which is a very unique product offer for the space market. It is originally a ground-up functional safety design, targeting the power steering and ABS systems in automotive, according to the ISO 26262 ASIL-D level. And now it's even helping the space missions to become very highly reliable at reduced cost. So that's a new innovation we brought here to the market.
Those are excellent examples, especially when you have described it in the background of the heritage that is actually needed in the space industry. Obviously, all this kind of makes sense. But as we know, in the space industry, the best performing technology isn't necessarily the most suitable option for individual mission. We also need to take into account how easy is it to design with a certain system or a component, how easy is it to integrate it and test it, and how much support is available from the supplier for the mission itself. So what is your offering in these areas to teams and missions?
Yeah, that's absolutely true. In space, it's not just about raw performance. It's easy of use, integration, testability, and even the supplier support can make or break the mission schedule. Those are areas where TI really stands out. Then let me give you some examples. First of all, we are focusing on making the component selection, sampling, and procurement as easy as possible. So customers can really access the right devices for their mission directly from TI.com. Another point, documentation. We ensure that all the radiation test reports, qualification data, which are important for the mission assurance and then risk assessments, those documents are also directly accessible from TI.com in the product folder. In addition to that, we are also offering a huge selection of design resources. Application notes, reference designs, white papers, and also to mention our E2E technical forum, where if you ask a question, our product line experts are answering directly to your question. So there are really people sitting behind and answering your technical challenges. And critically, I wanted to mention also, we back all this with one of the strongest and most experienced sales and technical force in the industry. And this ensures that the customer gets personalized mission-specific support through the whole program lifecycle. So to summarize, let me tell you this. We are not only providing components. We support the entire design and integration process, really helping customers go to the orbit faster and with confidence, and even making their products even stronger over the time.
This has been a very insightful conversation around the subject of standardized architectures. The final question that I have for you is, there are obviously several mission engineers out there that are probably today sitting on their drawing board looking at a future project that they have up and coming. What is your final message for those engineers that are out there, and what would be the key insights that you want to leave them with?
Yeah, I think I want to definitely point out that the space market adopts the attributes we know from automotive market, like modularity, design for test, etc. So there is definitely strong similarity, and we can really adopt many things from there. Nevertheless, there's still the need for dedicated products for space, because space is a very different and much harsher environment. And therefore, talking about space products, there is at TI, we have two levels, -SP and -SEP, to enable here the making sure you have the latest and greatest semiconductor technology in your hands for spaceflight available, giving you a good foundation and for your best and fastest innovation capabilities. And we want to strike out or underline the standardized architectures being a great enabler. And that goes hand in hand, right? We see this multi-programs, multi-mission profile support, therefore our 2 grades in SEP and SP, and making sure we can really be a long-term supplier for you, a reliable supplier, and make sure there's a strong benefit from the economies of scale. And last but least, it's the time axis, the time scale. Benefit of flight heritage. That is where in space we really need to make sure we understand that things will actually increase their value as they have been flying over the years in space. And this is where it's so important that as a semiconductor vendor, we give a very long-term supply commitment for the very same recipe, what we call single baseline. And that is very different over upscreening COTS devices, right? That if you are successful, you need to do more upscreening, need to find more devices. And this is where it makes the difference. If you're being held hostage by your past success, then you need to hunt for new parts, or you can enjoy a cash cow position and sell what you have developed in the past, happily enjoy the revenue and focus your efforts on your next generation and next innovation level.
Great. Michael and Adrian, you always bring some really refreshing insights to this podcast series. Thank you so much again for taking the time and talking very much in detail about the benefits of standardized architectures for space missions.
Thank you.
For all the listeners out there, TI's space portfolio is available on their own web store as well as their satsearch supplier hub. You will find the link for these in the show notes if you're interested in exploring their product portfolio further. Thanks for joining me today for another exciting story from the space industry. If you have any comments, feedback, or suggestions, please feel free to write to me at info@satsearch.com. And if you're looking to either speed up your space mission development or showcase your capabilities to a global audience, check out our marketplace at satsearch.com. In the meantime, go daringly into the cosmos. Till the next time we meet.